Hello, everybody. Welcome back to another video. Hopefully, I think this is going to be the last video that I will do on topic 8 and 18, which involves acids and bases. Maybe I'll do another video or maybe two more videos in the coming weeks. But with this video, I think I'll be able to tackle majority of the type of acids and bases questions that do come in exams. And as you can see, this question is pretty big. It's a 3-mark question, which we very rarely see in IB exams. Most of them are 1 mark or 2 marks, but very occasionally they're 3 and 4 marks. But as you can see, 3-mark question, and that doesn't necessarily mean it's difficult. So please don't let that scare you. That doesn't necessarily mean it's difficult. It just means that it's given more marks because they expect you to put forth more steps and use more knowledge in the question. Doesn't necessarily mean it's difficult. That's why you can see they've given a bigger box as well. I've seen questions that are worth 1 mark and are more difficult than questions which are worth 3 marks. So please don't let that throw you off in the exam. I know it can for some students, including myself. So this question is actually from paper 2 HL from May 2017, time zone 1. And in this, they have told us that hydrazine reacts with water in a similar way to ammonia. The association of a molecule of hydrazine with a second H plus is so small it can be neglected. And they've given us the equation of the reaction happening over here. Now, just by looking at this reaction, you can tell that the forward reaction for this, where hydrazine reacts with water, hydrazine acts as a Bronsted-Lowry base, right? Because it steals one hydrogen from H2O, it accepts it, and it becomes N2H5 plus, right? And in this case, in the forward reaction, H2O acts as the not Lewis, Bronsted-Lowry acid, because it donates a hydrogen and it becomes OH minus. And however, in the reverse reaction, it's swapped, right? The positions have been swapped because in the reverse reaction, N2H5 becomes the Bronsted-Lowry acid because it donates one H plus to OH minus, and OH minus acts as the Bronsted-Lowry base because it accepts this and it becomes water. Hopefully you can see that. I've explained this many times in previous videos as well. So if you have still have a few questions about this, please go and watch those. But in this question, they've told us that the pKb of hydrazine, which is N2H4, is 5.77. Now, I taught you in the previous video. Please, now I'm going to be linking a lot of things that I do in questions to previous videos. So if you haven't watched the previous video, I would highly recommend you to go and watch it. This is just the previous video that I did, or actually the second last video that I did. I explained how you can calculate pH from Ka. So how do you get pH from Ka? I've explained that in the previous video. In this scenario, we have been given Kb, or well, pKb, but it's very easy to convert from Kb to pKb and vice versa. And the only reason we put this P or we calculate pKb is so that the number is smaller, because Kb and Ka are often very large and messy numbers. So to make it more easier to read and understand, we just convert them into pKb or pKa. And even the same case for pH. We can actually just look at the concentration of hydrogen and determine the strength of an acid, but the number is extremely long. So instead we convert it to pH, which stands for potential of hydrogen, which is a smaller, easier number to read. That's literally the only reason. But anyways, now that we've got out of the way, we can use Ka values to get pH. What can we use Kb values to get? We can use Kb values to get pOH. What is pOH? I'm sure all of you have heard of pH and you're very familiar with pH. pH is potential of hydrogen. What is pOH? pOH is potential of hydroxide, because OH, right? And as you may have guessed, since pH tells us how acidic or non-acidic a substance is, pOH tells us how basic a substance is. So we have seen that in pH values, the lower the pH value, the more acidic the substance, right? The lower the pH value, the more acidic the substance. That's the general thing that we see. In pOH, the lower the pOH value, the more basic a substance is. So it's just literally the same thing, but it's flipped around, right? POH has an emphasis on basic solutions. pH has an emphasis on acidic solutions. So we can use Ka, which remember, Ka is the acid dissociation constant. And if you want to know more about it, please go to my previous or two videos before this and check it out. KB is the exact same thing. There is literally no difference. The process, the method, everything is the same. The same process you use to calculate the Ka, you use to calculate the KB. There is no difference. So if you want to learn how to calculate KB and how it's done, please go to my previous video where I explain Ka, and it's the exact same thing. But I'll do it anyways in this video so that you have understood what I am doing. Now, the first step that we have to do is we have to convert from PKB to KB. So we have PKB. How do you convert PKB to KB? Very simple. If you want to convert from PKB to KB, just 10 to the power of negative PKB. So in this case, we have 5.77. And if you put this into your calculator, or you have access to a calculator, this is a paper 2 question, you will get your answer as 1.698 times 10 to the negative 6. You see what a messy and long number, right? It's so difficult to say 1.698 times 10 to the negative 6. Instead, what scientists have done to make it simpler for themselves have just converted this. This is the KB value. They've just converted from KB to PKB because the number in PKB is definitely smaller, right? It's just 5.77, much easier to say. And how do you convert from KB to PKB? Well, it's very simple. You just do negative log of KB. And the reverse from PKB to KB, once again, let me tell you how to do it. It is 10 to the negative PKB. And you'll get your value of KB. Hopefully that makes sense. So now that we have got our KB value, what do we do with this KB value? Well, what does KB actually tell us? Well, KB is the base dissociation constant. And we use KB to calculate the strength of weak bases. Weak bases. What are weak bases? Weak bases are those bases which do not completely dissociate when added in water. And what I mean by this is that unlike strong bases, which completely dissociate, meaning they completely give out OH minus, weak bases, on the other hand, don't do this. They are weak, right? They can't give out everything. So you can consider them as weaker. They're typically, they don't have the typical effects you would associate with bases or acids. But in the end, it all depends on the concentration of the substance. But if you were to compare NaOH, which is a strong base, with suppose hydrazine, which is N2H4, and they both are of the same concentration, 0.01, 0.01, NaOH would be much stronger. So that's why it's called a strong base, and this is called a weak base. Now, if you want to really understand more about this dissociation, partial dissociation, incomplete, what do I mean by all of this, please go to a video that I made a while back where I explain what I mean by all this. Put a link in the comments below and you can go and watch that video and hopefully it'll help you. But anyways, we use, just to summarize what I said, we use KB to calculate the strength of weak bases. And likewise, we use Ka to everything the same to calculate the strength of weak acids. So like I mentioned before, I covered Ka in the previous video, so please go watch that if you have more questions about that. But for Kb, we're going to focus on Kb today. Kb calculates strength of weak bases. How do we use it to calculate the strength of weak bases? Well, we know that from what I told you before, that POH tells us how basic a substance is. So if you want to determine the strength of a weak base, we need to find out what POH is. And Kb can help us find out what POH is. And how does it do that? Because the formula for Kb that we use actually entails the concentration of OH minus. And all we need is the concentration of OH minus to calculate POH. Now, I know you may be a bit confused. You might say, well, they've given us the concentration in the question. They've told us that 0.01 mole dm cubed of hydrazine is used. So doesn't that automatically mean that 0.01 moles of OH minus will also be produced? And that would mean that we have the concentration of OH minus, so we can find POH. No, that's not the case. Remember, I told you that weak bases do not completely dissociate. If you have so if you have, suppose, 10 molecules of hydrazine, just imagine you have 10 molecules of hydrazine. Only 5, for example, only 5 of those 10 molecules will give off their OH minus. So it's incomplete. Not all of them are willing to dissociate. Now, this varies for different elements. Different bases, different acids have different extents to which they dissociate. Some dissociate more than others, others dissociate less. So that's what the Kb value helps us understand. What is the extent of dissociation? What is the dissociation constant? And in order to calculate Kb, we need to use the concentration of OH minus that is being dissociated or that is being produced by the dissociation. However, in this case, we are not given the concentration of OH minus outright, but we have been given the value of Kb, and we can use this to in turn calculate what is the concentration of OH minus. Hopefully all of that makes sense. I know it's a lot to take in. I'm very sorry if I've lost you along in the way, but please, if you do have questions about this, feel free to reach out to me on my social media or in the comments. I'll be more than happy to help you. So what is the formula for Kb? Well, Kb, how do you calculate Kb? So in a reaction, Kb is basically the concentration of all the products divided by the concentration of all the reactants. And in our case of this equation over here, our only reactants is N2H4. We ignore H2O. We don't take H2O into account for this. But so our only reactants, the only reactants that we have is N2H4. And what is the concentration of N2H4, which is hydrazine? They've told us. The concentration of N2H4 is 0.01. So we can put 0.01 over here. Now, we don't know what the concentration of our two products is. We don't know what the concentration of N2H5 is, and we don't know what the concentration of OH minus is. We have no clue at all. But in this case, we make an assumption. We make an assumption that the concentrations of both OH minus and N2H5 is the same. We make that assumption. That is one assumption that we make. We make a lot of assumptions in chemistry, as you've probably noticed, and this is just another assumption that we make. We make an assumption that the concentration of N2H5 and OH minus is exactly the same. So basically, we can write on top, if you want to simplify this, we can write it as OH minus squared, because the concentration of OH minus and N2H5 plus is the same. You can, if you're comfortable with it, you can also do this. But since we want to calculate what the concentration of OH minus is, I'm just going to choose to put OH minus here, OH minus squared, because we assume that the concentrations are the same. And if you multiply two things by two same numbers by each other, it's basically like squaring it, right? So we can put like that. Now, we know what the value of Kb is. We just calculated it in the previous part. The value of Kb was 1.698 times 10 to the negative 6. All we have to do is rearrange this equation to find out the concentration of OH minus. So we multiply both sides by 0.01. So this cancels out. We multiply this side also by 0.01, because whatever you do to one side, you have to do to the other side as well. That leaves us with OH minus squared. The concentration of OH minus squared is equivalent to this sum, the multiplication that I did over here. And the answer to that multiplication is let me just have some more space here, is 1.698 times 10 to the negative 8. So what is the concentration of OH minus? Well, we have to get rid of the square. So we take the square root of both sides. So OH minus, the concentration of OH minus is equal to the square root of this number. Sorry, the square root of this number. So we have to square root it, and we get our answer as 1.30 times 10 to the negative 4. That is the concentration of OH minus. Now that we know the concentration of OH minus that is produced by 0.01 mole dm cubed solution of hydrazine, you can see that 0.01 mole dm cubed of hydrazine does not produce 0.01 mole dm cubed of OH minus. There's a big difference. This number is way smaller than the concentration, or sorry, yeah, the concentration of hydrazine used. Hopefully you see what I meant earlier about incomplete dissociation or partial dissociation. Now that we have the concentration of OH minus, we can use this concentration to find the POH value. And you may be confused, how is the POH value going to help us find pH? Well, you'll see, don't worry, we'll get to that. So the concentration of OH minus was 1.30 times 10 to the negative 4. If you want to convert from this into the POH value, we have to take the negative log of this number. So you can just put this into your calculator, negative log of 1.30 times 10 to the negative 4, and you will get your answer as 3.885. So 3.885 is the POH of this solution of hydrazine. And as you can see, it is quite low. And like I said, low POH value means more basic. And you can see that hydrazine also is a basic substance. So hopefully that makes sense to you. Now that we have calculated the POH value, how are we going to get the pH? Well, by this formula, pH plus POH is equal to 14. This is a universal formula. It applies everywhere. And you can use this to calculate the value of pH, which we just have to do some simple rearranging. So pH plus 3.885, which is our value of POH, is equal to 14. Just rearrange. pH is equal to 14 minus 3.885, and that means pH is actually equal to 10.1. That's it. I know it's long. I know it's extremely complicated, and I'm so sorry if I lost you along the way, but I did my best to explain it to you. If you have any additional questions aside from this on how to solve such questions, please feel free to reach out to me. I'll be more than happy to help you. I'll spend time with you. I'll explain it to you, and hopefully that will make things better for you. But thank you so much for watching. I hope you all understood everything from this video. Please, if you're confused about what I have done, visit my previous video about Ka, and hopefully that will clarify some things for you. So please take your time, enjoy chemistry. I know this may be a torture for some of you, but really it is a brilliant, very beautiful subject with so much real life application. Thanks a lot for watching. I'll see you in another video with another question. Goodbye and take care of yourselves.